the largest void in the universe, is not simply empty space. It challenges everything we thought we understood about how matter arranges itself on cosmic scales. For years, astronomers believed the universe's structure was broadly uniform, shaped into a vast web of galaxies and filaments, but this immense region, stretching hundreds of millions of light-years across, appears almost hollow. This is not just absence, it suggests a limit in our models of cosmic evolution. Despite decades of mapping the large-scale universe, even our most advanced instruments cannot fully explain why such profound emptiness exists at all. When astronomers map the universe across billions of light-years, they do not see randomness, they see structure. Galaxies align along enormous filaments, like glowing threads suspended in darkness. These threads intersect at clusters, where thousands of galaxies gather under gravity. Between these luminous structures lie voids. At first glance, they appear to be simple gaps, but the largest of them is so vast that even entire galaxy clusters would seem small inside it. If our Milky Way were placed near its center, the night sky would look strikingly sparse. This is not merely a region with fewer galaxies, it is a region where the density of matter falls far below the cosmic average, across a scale that stretches the limits of comprehension. To understand how such a void can exist, we must return to the early universe. Shortly after the Big Bang, matter was almost evenly distributed. Tiny fluctuations, differences as small as 1 part in 100,000, were imprinted in the cosmic microwave background. Gravity amplified those small differences. Regions slightly denser than average pulled in more matter. Regions slightly less dense lost matter to their surroundings. Over billions of years, this process sculpted the cosmic web. This is the misunderstanding. The universe did not form as a uniform sea of galaxies. It evolved into contrast. Matter gathered into filaments. Space between them stretched thinner. Most voids measure tens of millions of light-years across. Some grow beyond 100 million. But the largest known examples approach 300 million light-years in diameter. At that scale, emptiness becomes structural. Simulations of cosmic evolution predict voids. They are expected outcomes of gravitational growth. Yet the most extreme voids sit at the outer boundary of those predictions. They are not violations of theory. They are stress tests of it. The James Webb Space Telescope was designed to look deep into cosmic history, observing faint infrared light from the earliest galaxies. Its sensitivity allows astronomers to detect objects far dimmer than previous telescopes could see. When Webb examines regions identified as voids, it tests a simple assumption. Perhaps these areas only appear empty because earlier surveys lacked sensitivity. Perhaps faint galaxies were hiding in the darkness. In many cases, Webb confirms the scarcity. The galaxies are not concealed by dust or distance. They are genuinely rare across enormous volumes of space. This does not mean the void is completely empty. Dark matter still exists within it. Gas drifts across it. Light passes through it uninterrupted. But compared to the cosmic average, the matter density is dramatically reduced. Another misconception emerges here. A void is not a hole in space. It is not an absence of physics. It is a region where gravity had slightly less to work with from the beginning. Over billions of years, that small deficit compounded. The result is not dramatic collapse, but quiet expansion. Voids expand faster than dense regions because they contain less gravity-resisting cosmic acceleration. As the universe grows, the emptiest regions become emptier still. At extreme scales, the largest void forces cosmologists to examine fine details of their models. The size and distribution of voids depend on dark matter, dark energy, and the rate of cosmic expansion. If dark energy drives accelerated expansion, voids should grow over time. Observations suggest that they do. Yet measuring this growth requires precision across billions of light years. The largest void therefore becomes a laboratory. Its dimensions test how accurately our simulations reproduce reality. Slight changes in the properties of dark matter or the expansion rate would alter the predicted number of such vast empty regions. This is where intellectual tension arises. The overall large-scale structure of the universe matches cosmological models remarkably well. The cosmic microwave background, galaxy clustering, and gravitational lensing all align within tight margins, yet the most extreme structures, including the emptiest voids, occupy the statistical edges. They remind us that cosmic evolution includes rare outcomes. The universe is not uniform, but it is not chaotic either. It is structured by probability, and at the far end of that probability curve, the largest void stands as a quiet boundary of expectation. There is a deeper perspective hidden in this emptiness. From Earth, the sky appears full of stars. From within a galaxy, space feels populated. But when viewed across hundreds of millions of light years, most of the universe is remarkably sparse. Galaxies are islands, clusters are cities, filaments are highways of matter. But the majority of cosmic volume lies in vast, low-density regions. The largest void is not an exception to cosmic structure, it is part of its architecture. The web exists because emptiness exists. Contrast defines the pattern. The James Webb Telescope does not reveal a dramatic rupture in cosmology. It sharpens the image. It confirms that even our most advanced instruments encounter regions where matter is profoundly scarce. The emptiest known region does not overturn our understanding of the universe. It refines it. It reminds us that small beginnings can lead to immense contrasts over billions of years. In the end, the universe is shaped not only by what gathers, but by what disperses. Matter collects under gravity. Space stretches under expansion. Between them lies vast silence. And in that silence, stretched across unimaginable distance, we see the quiet geometry of the cosmos itself.